Artificial Intelligence in Glaucoma, the novel, self-built, cost-effective and multimodal AI toolbox. No financial interest. We have heard about artificial intelligence and augmented reality working together. Is it just the hype or the real McCoy? Yes. It is real and is happening. This has revolutionized our lifestyle. Day-to-day activities that include the 2D or 3D face recognition tool used to unlock our mobile phone, fingerprint, iris scanner, etc. Unmanned robotic car with spatial recognition is another example. This technology also uses LiDAR sensor, ultrasonic sensor, camera, and radar sensor to visualize its surroundings and act accordingly. NASA's first large unmanned aircraft flight was also launched using artificial intelligence. Artificial intelligence performs much better than human beings in the image recognition field. Glaucoma is an image recognition field, which uses fundus photography, optical coherence tomography, etc. The artificial intelligence algorithm created by us uses a neural framework similar to the neural network in the human body. The artificial intelligence algorithm has to undergo the growth process similar to a human. We have used the medical image annotation tool called the Visual Object Tagging Tool, VOTT. The first step is annotation, which is the action of marking a text or diagram. Previous studies didn't clearly explain the black box dilemma. A question was raised: what is inside the black box of artificial intelligence? The rationale behind the predictions of AI are not clearly understood. This is how our AI is trained. Fundus images are collected randomly and then it goes through the annotation process using the VOTT annotation tool. Further, it goes into the annotation dataset, then into the SANS-10 AI toolbox where the AI makes its prediction, which is in turn validated by humans. The incorrect predictions go back to the annotation step and the process is repeated. This is the annotation process in which the disc is marked and annotated. Similarly, the normal macula. Normal vessels. Glaucomatous cupping. RNFL wedge defect. Bayoneting sign. Disc hemorrhage. Peripapillary atrophy. Tilted disc. Etc. This is the final output after the complete annotations. Intersection over union, objectness loss, and classification loss showed better results after each test, with improvement in precision, recall and minimum average precision values. These are some of the predictions made by our AI tool, predicting not only the diagnosis, but also the intrinsic signs, thus making it an explainable AI. We have worked on an explainable AI model and evaluated its interpretability. Sensitivity is 96.4% and specificity is 100%. In this research, we have utilized true-color confocal fundus photography, which yields good quality high-resolution images, thus improving the interpretability. We have also explored the application of artificial intelligence in angle assessment, which was more effectively interpreted by multimodal imaging techniques. Here is the schematic plan of how the AI assesses the angle. This flowchart illustrates the process of angle annotation. The scleral spur, which is the thickest part of the sclera, is designated with a yellow mark. The trabecular meshwork, which is marked as green, is located 500 micrometers from the scleral spur. The iris point is the location on the iris, where the perpendicular drawn from the trabecular meshwork point meets. The apex is where the cornea and iris converge. A line is drawn from the apex to the point on the iris and trabecular meshwork, which forms the angle. A protractor is used to measure the angle. An angle less than 15 degrees is regarded as narrow, whereas more than 15 degrees is considered open. Closed angle refers to an extremely small angle. The final annotation of the angle is done using the bounding box tool. We aim for multimodal angle annotation using artificial intelligence. Final angle annotation done in a UBM image. Angle annotation done in Anterior image. Angle annotation done in an AIOCMTC image. Angle annotation done in SchemeFlug image. After several training process, the AI model attained growth. Artificial intelligence and augmented reality can be incorporated for simulative glaucoma learning. We have innovated a software named IMG Holo in Microsoft HoloLens for simulative learning, teaching, counseling, and diagnostics. In this video on the right-hand side, you can see the person using the HoloLens, moving his hand in thin air, and the left-hand side part of the video shows what he actually sees through the HoloLens. The eyeball model created by us using a real fundus image with splinter hemorrhage is being demonstrated. The user can rotate and zoom the model accordingly. Similarly, the angle structure can be viewed. Also, there are models showing the RNFL defect. Practicing in the ophthalmic metaverse. The novel, self-built 3D simulator. With the use of hand tracking in the HoloLens, a simulative training module is created. The 3D eyeball model gives a real-time simulation of the angle structures to practice the implantation of the eye stent. During the simulated training, on proper implantation of the eye stent into the trabecular meshwork, the indicator lights up as green. This training improves the agility of the doctor for the implantation of the eye stent in the angle. During the inception of AI or AR, the expectation is similar to arm wrestling between doctors and AI. But the reality is that doctors and artificial intelligence need to work together for a better humanity, where AI helps in screening and the final diagnosis is done by the doctor, thereby increasing awareness among the community and helping in treating and curing the human population. Our novel, self-built, innovative AI tool workflow in glaucoma diagnostics. The imaging done using the image capture devices goes through our AI software, and then within 60 seconds, with no chair time, the glaucoma diagnosis and interpretation is done. Artificial intelligence and augmented reality are the future of e-ophthalmology. Thank you.